So another technique that was used for 2D modeling for many, many years, and is still something that people use because it's a good way to visualize flow, is the stream function. So the stream function is a 2D technique where you define u as d psi dy, and psi is always the symbol for stream function, so it's this thing that looks like a pitchfork. That is d psi dy is u, and d psi dx with a negative sign is v. Those are convenient because, again, if you look at the 2D conservation of mass equation, so we have du dx plus dv dy is equal to 0. That's incompressible two-dimensional flow, and we plug in, this here and this here. Let's see what happens. So we get d by dx of d psi dy plus d by dy of negative d psi dx, which equals what? Well, this equals d psi, that's d squared psi dx dy minus d squared psi dy dx. That is, these are the same. Smooth continuous functions, the order of derivatives does not matter. So those are 0, which means they satisfy the conservation of mass equation absolutely in all conditions. So as long as the flow is incompressible and you use this definition, the stream function, you automatically satisfy continuity. So stream functions always satisfy what we call continuity or conservation of mass. So that's nice. That's a feature. You don't have to worry about the conservation of mass equation. It's already dealt with. If the flow is irrotational in 2D, we know once again what that means. That means dv dx minus du dy, which is the vorticity, is going to equal 0. So that's what irrotational flow means. Again, we're going to plug in our u and our v. So we're going to plug in u for that, plug in v over here for that, and we're going to see what that has to say. So dv dx is the same as d by dx of negative d psi dx and minus d by dy of u d psi dy is equal to 0 according to that irrotational flow theory. So you look at that, that comes out to be the second derivative of psi with respect to x with a negative sign minus the second derivative of psi with respect to y with a negative sign is equal to 0. I can just multiply that by -1, and I get d squared psi dx squared plus d squared psi dy squared is equal to 0. What's that? That is once again the Laplace equation. So I have a second way to model flow using the Laplace equation. As I said before, the Laplace equation is a very well-studied equation with lots of lovely solutions already dealt with. So this is a second way to use the Laplace equation to get fluid flow, a different way. It's going to have different boundary conditions, so it's going to give you a different solution than the potential flow theory would. And you're going to end up with another function that's going to give you the velocity field. Once again, it's irrotational. Let's see here. If we have a solid surface, we're going to know what the boundary condition is for that. In that case, solid surface, well, we know that the solid surface has no penetration, no slip. So psi is going to be basically constant. So on solid surface, psi is constant. So that prevents any penetration or slip. It's actually a no slip condition on the so that says u equals v equals 0 leads to psi is constant. And the other thing is that and you would still have your known boundary conditions on the boundaries. You would know d psi dx. D psi dx and d psi dy would be known on boundaries. So actually, no, psi is constant is a no penetration condition. You can have slip. So psi is constant means no penetration and no flow in or out of the surface. You can still have slip because you could have a d-side normal to the boundary could be non-zero. That would give you a flow parallel to the boundary, but d-psi, but it has to be constant because d-psi in the direction of the boundary would give you the vertical flow that would go in or out of the surface. So solid surface psi is constant, and you have to know your d psi dx and your d psi dy in order to have boundaries and solve this Laplace equation. So you have a second way to do this for incompressible irrotational flow using the Laplace equation using stream functions. So now we'll see how those two things relate to each other.